In Lesson 3-5, we will be modeling with nonlinear regression. In video 3.5.3, the learning target is for students to model data with exponential, logarithmic, and logistic functions. In this video, we will be discussing logistic growth functions. A logistic growth function has the form f of t equals c divided by 1 plus a times e raised to the negative bt, where t is any real number, a, b, and c are all positive constants, and c is the limit to the growth. Okay, a logistic function is one that starts out almost exponential, right? You can see this graph right here. It starts out like an exponential growth function, and then eventually it just flattens out at the top. It reaches a limit and then ends up staying constant. This happens sometimes like in a city, where a city experiences population growth for several years, and then eventually that growth kind of subsides and it just stays constant. So that would be one example, real world example, that could be modeled by a logistic growth function. One thing to note is that the value of e in this equation is the irrational number that is approximately 2.71. So in a natural log, it's base e. Here in this logistic growth function, there in the exponential term here in the denominator, e is still that irrational number, approximately 2.71. In the real world example 3, we will be discussing logistic regression in terms of advertising. The number of television ads for a certain product affects the percentage of people who purchase the product as shown in the table. Use logistic regression to find a logistic, not logarithmic, logistic growth function to model the data. Then use the model to predict the limit to the percentage of people who will purchase the product. So in this example, they give us a data table, and here is on the left side is the number of ads, so we'll let that equal x, and the number or percentage of people that then purchase the product is y. So what this table is stating is that if an ad runs 90 times, like let's say a television commercial, that's a type of advertisement, then 49% of people would buy that product. As you can see, as the number of advertisements increase, the number or percentage of people rather also increases. So it's going to be a growth function. Well, they told us that. It's a logistic growth function in the problem. And so what we're going to do is we're going to go ahead and enter this data into our lists. Remember, the lists are under stat on our calculator. So if you press the stat button and then edit, we're going to enter the ads, number of ads, that's going to go in list 1. That'll be list 1. And the percentage of people is going to go into list 2. Once we have our data entered into our list, our next step is to make sure our stat plot is turned on. So under y equals, if you press second and then y equals, you'll see your stat plot. Make sure plot number 1 is turned on. Right? We want plot number 1 on. Make sure your lists are L1 and L2 if that's where you entered your data. And then the next step would be to set up our window. Now for window, in this example, we could say that x minimum is 0. Our x maximum, we could say 100. Our x scale could be 10. And we could say y minimum is 0 because that's the percentage of people that buy the product. And y maximum could be, let's just say 60 in this case. And we'll say our y scale is equal to 3. At this point, after you have your window, you can press graph and you should see your scatter plot. Based on the scatter plot shown here, you should have something similar to this. The only thing we did slightly different than the textbook is that we made our scale 10 and they used a scale of 5 on the x-axis. So under step 1 here, we're looking at the scatter plot of the percentage of people who purchase a product after X number of ads. And the scatter plot of the data resembles the graph of a logistic growth function. It increases and then eventually we would assume that it kind of tapers off. That no matter if we ran an ad 1,000 times, you're never going to get 100% of people to buy the product. So we're going to go ahead and use a logistic growth function because we're assuming that over the course of time that percentage of people buying the product is going to kind of level off. So now that we need to calculate our logistic growth function, we have our scatter plot, we have our data entered, we need to now calculate our model. So to calculate a logistic function, we're going to go to stat, which is right here, right? But this time instead of choosing edit, we're going to arrow over to the calc underneath the stat menu. So arrow at the top of the stat menu, it says edit, and then the second word is calc. We're going to arrow over to the calc menu, and underneath the calculate menu is going to be various different types of regression. And we want to choose the logistic function, which is option B. You have to scroll down quite a ways to get to the logistic function. It's almost at the very bottom of the menu. It says logistic, and then it's option B. There's a B letter next to it. And if we if we choose or enter on logistic, then we have to tell the calculator, based on your operating system, is going to be a little bit different. I kind of have the old school operating system. And it's going to bring me back to my main screen, and then I'm going to tell the calculator list 1 and list 2 because that's where my data is stored. And list 1 and list 2 have to be separated by a comma, which is right here. And list 1 and list 2 are right here on your calculator above 1 and 2 on the keypad. So from there, I can press enter and it'll give me my logistic equation. Those of you that have the new operating system, when you enter on logistic, it'll bring you to a screen and you can just make sure your lists say X list is L1 and Y list is L2, and then you can press calculate. So we're going to calculate our equation. So press enter and it's going to give you the logistic equation. The equation the book got when they calculated the logistic equation is P of X equals 55.86 plus, or divided by 1 plus 50.24e raised to the negative 0.064x. Now some key pieces in this equation are this C value on top. C is the limiting portion or limiting percent of this function. So what that is saying, that top number tells us where this function is going to flatten out. So basically what they're saying is it doesn't matter how many ads we show, eventually the percentage of people buying the product is going to level off, and it's going to level off at 55.86%. And our A value was 50.24, and our B value was 0.064. And in the equation, you have to put a negative in front of that B value. So they're showing you that right here in the equation. They outline what the general equation for a logistic function is, and they're saying take the opposite of B and then multiply by X. So since our B value is positive down here, they put the negative sign in front of it to take the opposite value. Now that we've calculated our regression equation, I want to copy and paste that equation into my equation editor. So to do that, I'm going to, step 1 is to go to y equals, select y equals, and underneath y1, you want to make sure to clear out any previous equations out of y1, and turn off any other equations, y2, y3, y4, that you have stored in your equation editor. You can do that by unselecting the equal sign, or just clear out all the equations in your equation editor. Step 2, once you have your cursor in y equals, right, under y1, we could put our cursor there, and then after we clear out the equation, if you had one there, we're going to select vars, which is on the right side of our equation, right here. We're going to select the vars button, and in the vars menu, we want to choose option number 5, which is statistics. And option from there, after we choose statistics, we have to arrow over at the top and choose EQ. We're going to go to the EQ or equation menu. And then under that EQ menu, option number 1 is Reg EQ. If you select Reg EQ, it'll take your logistic regression model that you came up with, and it'll paste it into your equation editor. And then after that, you can press, after your equation's been pasted into your equation editor, you can press graph. What this will do, it'll graph your equation over the top of your scatter plot. Now that what you should see is that your logistic function is a very close fit to the data on your scatter plot. It fits the data very well. It's not perfect because the logistic equation does not go through the center of each point, but the points that it doesn't go through the center, those points are very close to the logistic model. You can see this point right here, as the logistic equation does not go directly through the center of that dot, but that dot is touching the side of the logistic model, and so therefore the R value for this model would be very high. It would be probably in the high 90s. So what we have here is a logistic model that we know fits the data well, and next we are going to use that to predict what will happen when, let's say, 100, 1,000, 2,000, 5,000 ads are shown. What is the limit to this data? What is the limit to the percentage of people buying this product? Now, what you could do is you could graph this equation, and then you could change your table settings. Under your table setup, you could change that to ask. You could change your independent variable to ask. Right? Your independent, you can change that to ask. And if you go to your table, that allows you to plug in whatever you want for X. So you could type in 1,000, 2,000, 5,000. You can let X increase infinitely, right? You can let X get really big, and then see what happens to your Y value. According to this model, the Y values should taper off and end up staying pretty constant. So what you're basically doing in a logistic model, since a logistic model tapers off, is that you're really finding the right-hand limit. So the end behavior of this function. You're finding the limit as X approaches infinity. What is your limit? What is your Y value approaching? Well, according to this type of function, your numerator is the limiting percentage. So that C value is the amount or the limit as x approaches infinity of the function is going to be given by that C value, which is your numerator. So your highest percentage, no matter how many ads are run for this item, it will never reach 56% because you're saying that the limiting percentage is 55.86. In the guided practice for example 3, the probability of a person liking a song increases with the number of friends who say they also like the song. The data shown in the table models this situation. Use a logistic growth function to determine the limit to the probability that a person will like a song based on the number of friends who say they also like the song. So given this set of data, in this case the number of friends is x, the probability or percentage is y. I would like you to go ahead and find a logistic growth model that models this function, and then use that to determine the limit to the probability that a person will like that song based on the number of friends who also say they like the song. You have 4 choices, A, B, C, and D. Go ahead and find your logistic growth function and choose answers either A, B, C, or D, and then press submit.